This is Violent Crumble, a fully 3D printed combat robot. Yes, even the weapon blade is 3D printed, and it hits hard. Plastic combat robots are a brand new class of machine where limited material choices combine with the freedom of 3D design to create a brand new engineering challenge. And in this video, I'll show you how I designed and built this micro-sized monstrosity and how it performed in the arena. I mean, it's just plastic, right? How destructive could it really be?
Oh, it's gone very quiet. Not quite enough.
But first, the obvious question, why plastic? Well, a few reasons. Combat robotics as a sport has evolved a lot since its inception over 30 years ago, and even tiny weight classes are dominated by sophisticated machines made from aerospace materials like titanium. They're an incredible design challenge, but not exactly easy to get into if you're just starting out on a shoestring budget, which is where the concept of plastic combat robots comes in. The specifics vary between local competitions, but the idea is to restrict material choices to easy to print filaments which are strong enough but can still break in a satisfying manner if you hit them hard enough. These include plastics like PLA+, ABS, and PETG, but not the stronger, more challenging materials like TPU, polycarbonate, or nylon. This means that the strength of your bot's armor and weapon depends more on your design choices and slicer settings rather than who can afford the most expensive super alloy and machining process. And hey, if your bot does get annihilated, who cares? Just print more parts, repair the damage, and you're ready to go again. Our local rules also prohibit the modification of any hardware, which means all the nuts, bolts, and bearings must be easily accessible off-the-shelf parts. You could literally build these bots in a bedroom, and I was skeptical at first. Surely it means they're pretty boring, right? Well, was I wrong? Plastic combat robots are awesome to watch fight, so I just had to give it a go. And Violent Crumble was my first crack at it. These bots can only weigh a maximum of 150 grams, so they're classed as UK ant weights, then also known as fairy weights in the US. This tiny size also helps keep the cost down and makes building them easy, if a bit fiddly at times. The design is loosely based on this low-cost horizontal spinner design I made in a previous video, but it's been modified to be constructed solely from 3D printed plastic. These are all the bits that go into it. It uses a Malenki Nano as the combined receiver and drive speed controllers, 2 N20 gear motors for drive, a super cheap brushless motor from AliExpress paired with a 20 amp BL Heli S brushless ESC for the weapon disc, and it's all powered by a tiny 195 mAh 2-cell lithium polymer battery. This parts list is a great choice for your first basic 150 gram ant weight spinner, plastic class or otherwise, and you can find more information in the video description below. With the material restrictions, design considerations really matter, as do slicing settings. You want to squeeze as much strength out of every element, and that's where I found the really satisfying challenge of this class comes into play. How do you make weak materials strong? And how do you create a weapon blade out of the same material you're going to be hitting it with and have it stay in one piece? Because the class is so new, these are problems that are still being solved. That's what makes it really exciting. Going with the theming, I really wanted Violent Crumble to look the part. After all, being able to create gaudy, multicolored plastic bots is almost a prerequisite for the plastic ant weight class, so I created this multicolored part by creating the text as a vector and importing it into Fusion as an SVG. I've done a whole tutorial on this process if you're interested, but in short, you need to separate each region in a way that your slicer can understand and then assign color to it. To achieve this, I did an extrude cut down into the part using the SVG as a guide, but only by a tiny amount, like 0.05 millimeters, which is enough for the geometry to be preserved on export to the slicer, but not enough to actually show up in the final 3D print. These tiny cut regions make it easy to paint in color using the fill tool within Orca Slicer, which is assigned to different filaments. I've been saving up this gorgeous Galaxy Purple PLA Plus from Prusa for some time, and it was pretty much made for this project. I love the color and the shine that it gives off. I combined it with Snapmaker's red basic PLA and some eSun yellow PLA Plus, and the resulting part looks absolutely stunning. I know that in the past I've made many comments on how silly multicolor printing is, but that was mostly in context of single extruder AMS systems that waste a huge amount of time and material when purging between color changes. But in the context of a tool changer setup like the U1 and Prusa XL, the waste is marginal and tool swaps take place in a matter of seconds. So I feel much less guilty using it to create those fun 3D prints for a combat robot class that doesn't take itself too seriously. Like the rest of the chassis, the robot's weapon also needs to be made from plastic, one of the ones that's listed available in the rules, which sounds quite frankly ridiculous, but it adds so much of the weirdness that makes this class so fun and refreshing. Again, how do you hit something made out of the same material and break it, but not yourself? Out of all the material choices available, I decided that solid PLA Plus would be the best option. It's dense and super hard, but should still have a little give before shattering. This was my first pass at a blade, a super aggressive single tooth with a large counterweight behind it, bolted directly to the brushless motor. At 9.5mm thick, it's a chunky boy, and I printed it with a 100% infill because I thought that the alternating pattern would be the strongest option. Spoilers, it wasn't, but we'll come back to that. For the wheels, I went with my new favorite foamed TPU dual material printed ones that I used on Vortex. They took humongous hits and yet they survived, and they have pretty good grip too. Initially I thought that having a super wide drag style tire would be pretty funny, but it was really heavy, and eventually I came to my senses and reduced their thickness for competition. But just a quick note on these foam wheels, they're no longer legal in our competition here in Australia, the plastic antweight class in New South Wales, because foam turned out to be pretty effective as armor in itself, and thus kind of boring, but I will still use these wheels on my open class robots because they are indeed very durable. Wiring the robot up was, as usual, fiddly, so good soldering skills are a must, but honestly, this design is pretty basic. As long as you pay attention to the wiring diagram and take care to plan your circuit and wire lengths, it's not too bad. Rules require that the robot can be safely turned off and on, and you need to be able to tell if it is on with a LED. So I added a small screw switch to the circuit, which was probably the fiddliest part of the wiring, honestly, but once that's done, we're good to go. I can't quite recall where these particular N20 gear motors came from. There's so many different flavors with different RPMs and power outputs out there, but these ones are real screamers. It drives fantastic, especially with the TPU Air wheels. But it's so fast, I know it's just going to never hit its top speed in the tiny arena. And the asymmetric weapon disc seems balanced, which is a win, so it was time for its first competition. Let's put it in the arena and test it out against some willing sacrifices. Opponents. But first, I want to thank PCBWay for sponsoring this video and many of my combat robot builds on this channel. If you can design it, they can make it from a huge range of materials, like this custom hub motor I designed, and they machined from solid titanium. There's no way I could have made this part any other way, and it hit hard. Recently, I've been pushing my skills into PCB design, which is very new to me, and I got these custom boards made, which actually form part of the robot chassis, but they have integrated traces for a switch and LED. Circuit boards don't just have to be simple squares, and PCBWay can crank these out really fast, and they make an excellent budget alternative to carbon fiber for combat robots. And you can use the code PCBWay-MakersMuse10 to receive $10 off any order of $30 or more. So why not give PCBWay a go for your next project? You can find more information in the video description below. Now, let's go back to the Crumble. Violent Crumble's debut was at the end of 2025, along with Vortex, which was my open class antweight, to test PIBA, which turned out to be an incredibly viable, tough, and lightweight material for that class, but it's definitely not allowed in the plastic antweight class. Having thrown both rubbers together at the last minute, there wasn't really any much testing or driving practice involved, so its first fight against Duo Flipper, a little lifter, I was pretty much going in blind.
Starting in 3, 2, 1, fight. Okay, how good those foam wheels grip.
Whoa!
We put that in. Yeah. First blow.
Oh!
Take the James approach, just pin the throttle.
I respect the arena more than him.
And your batteries.
Ow.
Go on.
Right, so when it's actually spinning, controllability is next to zero. But aside from that shamefully bad driving, Violent Crumble got some pretty good licks on Duo Flipper, which broke it enough for them to tap out. It's a promising start, but the next fight against Chomp, a control bot driven by the daughter of one of the competitors, went, very differently indeed.
Get him! Oh no! Get him, Benny! No! Fatal! No!
Yep, she done exploded. Learning from the previous fight, I tried a different driving strategy of short bursts before recalibrating, and it worked much better until the first major contact sent Violent Crumble flying and ricocheting off into the floor, literally snapping it in half. Not the weapon blade, the whole chassis. I thought there was enough material around the motor mount, but evidently not. It sheared clean through and turned the bot into a hobbling mess. From this point on, it was just a waiting game till the pit opened, and my bot was properly and rightly so pushed right in. The third and final fight of the event was against Randall, a big vertical spinner. This is a classic destructive matchup, and it did not disappoint.
Starting in 3, 2, 1, fight! The weapon exploded.
And there it goes. Violent Crumble tore the entire weapon off in one big hit, but the PLA tooth snapped clean off in the process, resulting in both bots being able to do much of anything until the pit opened and we both skated down it. So this little thing has promise, but it has to stop breaking itself in half every major hit, and I need to find a way of strengthening that PLA blade. And with the next competition a month away, it was time for a redesign. For the chassis, I decided to try another filament altogether. The Prushiment Galaxy PLA is gorgeous, but the way it cracked apart is somewhat unusual. PLA Plus is usually a lot more chewy in my experience, so I suspect the addition of all the pretty sparkled and pigment is resulting in a harder, more brittle material, but that's just a guess. Instead, I'm going to switch to ABS for the main chassis. Years and years ago, I actually made a video saying that ABS was dead, at least in 3D printing, and it kind of is. It's difficult to print without warping, and in some cases not even as strong as modern PLA+, but it does have one major advantage: its density. PLA has a density of around 1.24 grams per centimeter cubed, which makes it quite heavy, especially when you're printing thickened walled parts for strength reasons. ABS, however, has a density of around 1.04 grams per centimeter cubed. That's a significant difference, and at this scale, it means I can thicken up the chassis even more and add more armor without going over the weight limit. I'll leave the top plate just how it is though, because that is way too pretty to change. Looking at the old chassis, you can clearly see how the crack at the front took the path of least resistance, following the bolt holes to break at the thinnest section. So thickening up this area was my first priority. I increased the wall thickness around the motor cavity from 3 to 8mm, more than double, and I added even more material to the motor support underneath it. I also decided to thicken up the entire base and just print with a bit of infill instead of the original offset design, which needed a lot of support material and it was kind of annoying. The plastic ant weight class is still being refined, and as I mentioned before, foam wheels are no longer allowed, which is fair enough because again, they can be effectively used as armor against plastic weapons. So I swapped out to thinner but much more fragile printed wheels which use O-rings as tires. These have decent enough grip, I've used them before, and the O-rings are really cheap and come in a huge range of sizes to suit your design, but one good hit and those wheels are toast. So with a lineup of nasty spinners entering into the upcoming competition, I finally decided to add something everyone has been shouting at me to do for ages. Wheel guards. These wheel guards start out thick and high before tapering down to the front of the robot. They could be higher around the wheel and then taper off abruptly, but I think they would just look ugly, so instead I decided on a nice smooth transition. Ever the industrial designer. The original asymmetric weapon blade hit hard, it even damaged the wood on the sides of the arena in some impacts, but it also broke, shearing right across the infill lines, so that needs to be improved. With the entire robot printed and the guts transferred over, there was actually a whole 30 grams available for the new disc, which is pretty crazy. So I went all out with this new updated shape. I thickened up the tooth substantially and gave it a less aggressive profile, but those slicer settings still need tweaking. As I mentioned, I previously did a 100% rectilinear solid infill, but a close-up photo of the cracked blade shows how the tooth just sheared along that infill direction. So I thought that maxing out perimeters instead would be the way to go, because that's what I've heard from a few other builders. It's definitely better, but early testing revealed an annoying behavior where the perimeters wouldn't hold together on impacts, almost like the disc was shedding its layers one by one each hit, instead of acting like a solid lump of plastic. I want the blade to deform and round over, not just crack apart. So that begs the question, what slicer settings make the strongest 3D printed part? Well, along those lines, I really wanted to test out this brand new slicer called Pre-Flight, which has a lot of really interesting features I've not seen anywhere else. It's built on Prusa Slicer and the open source Slicer engine, and the main selling point is the ability to overlap regions using their Athena perimeter generator. The idea is similar to bricklayers, but instead of using Z height differences to pack in more plastic, it does something called interlocking perimeters, which over-extrudes offset solid infill with the aim of the additional material squishing into the gaps to form a more homogeneous solid. It's very cool, but I couldn't get it to work at all with any of my printers, which really sucks. The slicer has no profiles as it's currently in alpha, fair enough, but all of my attempts to import printer and material profiles from either Prusa Slicer or Orca Slicer failed. And even though I could eventually get some settings in, it would throw errors with the start G code, and even when I resolved that, the printer itself just flat out refused to run the G code. I'll keep trying and definitely report back, but for now, it's not exactly usable in my experience. However, with that concept in mind, I arrived at these somewhat similar settings within Orca Slicer. You can force a similar offsetting effect by changing the extrusion widths of internal perimeters and solid infill lines and enabling alternate extra wall. Ideally with the extrusion widths, you'll have a multiple of 2, which will move the extrusion lines between the valleys of the previous extrusion layer. And I made sure to turn my solid infill to concentric. You can't control the over-extrusion of independent parts of the model like you can in Pre-Flight, but by upping the solid infill to a nice and thick 0.8mm extrusion width, it seemed to work pretty well. Finally, I forced a little bit of over-extrusion on the outer surface of the part by increasing the infill/wall overlap. But be careful with this one. I tried 45% and it created this smeared failure. I would aim for only the slightest hint of over-extrusion so you don't lose dimensional accuracy, like maybe 20-25%. Just adjust it to taste. Finally, I figured it couldn't hurt to turn ironing on for the top surfaces, and I made sure it ran perpendicular to the solid fill. Does it make the part any stronger? No idea, but it sure does make it look nice and smooth. And coming in at 30 grams apiece, they're among the heaviest blades in the plastic ant weight class right now, and they sure do feel solid. Ow. So I think it's time for a test to see if this little motors can even handle these heavy weapon blades. Let's just say the first test didn't quite go to plan. Yes, guess who didn't tighten down their motor screws? This boy, right here. Yeah, don't leave your bot building till the night before the event. You'd think I would have learnt that by now. With the motor actually secured to the chassis, however, I was able to properly get it up to speed, and it's pretty terrifying. It was also at this time that one of the drive motors decided to die for no reason, so I cracked the robot open and got rid of the cheap unknown N20s and modified the design slightly to accept the much more powerful but shorter N10s from Wranglebots. The gear motors aren't actually secured to the frame in any way, they instead rely on locking features in the chassis and top plate that sandwiches them in place, so a last minute printed spacer solved that. Seriously. Think about it, what other technology lets you iterate as quickly as modern 3D printers? I designed these spacers, went and had a very late dinner, and they were ready and waiting for me when I was done. I also threw in this little custom tool, which proved invaluable in repairing this little bot when the event came by. See if you can guess what it's for. And with that, Violet Crumble 2.0 was complete, and it looks quite nasty, if I do say so myself. So it was off to Robot Royale at the University of New South Wales for the first event of the year to face off against no less than 16 other plastic class combat robots with its first fight against Anthony Flippanese, a compact and well-armored flipper. The pit will open 90 seconds into the fight, so I've got that long to try and knock him out, or it's all over. Here's how that fight went.
3, 2, 1, go.
What is happening? No, but they want to go
It's got a second cover on the inside.
Oh. I don't know why he's still... The only way that one was they both have the flip thing, so he has to stay. Oh!
Crazy stuff. They'll probably win like the...
It's going down in 20 seconds. May change this.
Hello, Pancake.
Can you move?
Whoa!
10 seconds to the pit. 5, 4, 3, 2,
Like, no.
1.
He's so funny. No, but what
Brave choice.
You might like think it's like to do something
Oh, I got the weapon! That's the whole can.
Well, that's new. Never have I ever considered that a plastic combat robot could be so violent that the motor itself would shear in half. With both bots completely hobbled, it did become a pushing match, which is one that my robot is not designed to win. But I did manage to avoid going down the pit, so the fight went to a judge's decision, which was a very close win to Anthony Flippanese due to superior control. Oh well, I'm actually pretty happy with that because this robot is clearly capable of high levels of damage, so I got 2 repairs. Thankfully, I had plenty of spare drone motors, but the whole process meant I had to unscrew the old one, desolder the wires, and remove the disc from the broken off motor, which is why I am oh so glad I printed this little motor can clamp to easily undo the nylon nut, which tightens against the motor's rotation to hold the disc in place. And yeah, it gets quite tight indeed. I would not have been able to get it off without this little tool, so I'm glad I thought of it. With my bot fixed, it was time for my next opponent, Flipside, another well-armored lifter. Now that I know that these motors have a very limited lifespan, I took things a little bit more carefully and I didn't go full throttle. Nonetheless, the results were quite spectacular.
2, 1, go!
Oh!
Should have seen that coming.
Not my face.
Violent Crumble is the winner.
Flipside tapped out after losing the entire front of his bot, and I thought I escaped unscathed, but when I was playing with the weapon motor, it felt a little bit wobbly, and then...
Yeah, that's normal.
Still good. Put it back on. Yay.
Yep, another shattered shaft and another dead motor. This would sadly become a theme, with its next fight against another lifter over easy, starting out strong, but once again failing in spectacular fashion.
Well, who could have seen that coming?
Okay, so by this stage, it was pretty obvious that these $2 drone motors don't like smashing into things with a huge asymmetrical plastic blade. Who would have thought? But it just so happens I still had this, a much higher quality motor that has the same profile and bolt pattern. These motors literally are called ant motors. They got them on AliExpress. They don't exist anymore, but I actually used them in my robot Pancake years ago, so I know they can take quite a beating. So I threw them in a desperate attempt to keep Violent Crumble from crumbling so quickly. And despite the robot's failings, I did actually make it into the finals. Well, at least the runner-up to the finals, because so many other robots were tied on points. So I had to do a tiebreaker, facing off once again against Flipside and a nasty vertical spinner called Train Pain. And this new weapon motor, it's the business.
Spinner at first, but then it's not.
Oh my god!
It's gone very quiet.
Not quite enough. Yeah. Okay. Oh, I'm screwed in the.
Yeah, just go grab it.
I don't like that pit.
In all my years of fighting combat robots, I have never once seen one robot literally screw itself into the floor and get stuck. I am shook at that loss. It took Violent Crumble out of the competition, and it's done. But at least it did so after leaving a trail of utter destruction in its wake. Because I'll be honest, I was pretty skeptical about the concept of a plastic combat robot class, especially one that limits your material choices to those that aren't really that strong, but that's entirely the point. As I mentioned at the start of the video, combat robotics has become incredibly competitive globally, and it takes a long time to learn all the things that go into a competition-winning bot. Chassis design, weapon design, fork design, center of mass, balance, reliable wiring and soldering, driving skills, and so much more. If you invest all of your time and money into your first combat robot just to have it destroyed instantly, you might learn how to fix a few of those things, but too many expensive setbacks and you might just give up. With plastic ants on the other hand, the worst that'll happen realistically is your chassis or weapon will be destroyed. you're very unlikely to lose a drive motor. You can reuse the battery and speed controllers again and again as you refine your design. Anyone with a 3D printer can create one, and the additional layer of decisions when it comes to the slicer settings is something that I'm personally finding really fun to an almost addictive degree. These little things are a fantastic engineering and design challenge, and when you get that itch to build something bigger, which is something I'll still be doing, you can take all of that learning and apply it using services like PCBWay to create parts from metal and carbon fiber, take your robot to the next level and put it to the test inside the arena. After Violent Crumble was out of the competition, I entered into a grudge match against a full body spinner and Radial, a ring spinner that moves around on shuffler pods to give it a 50% weight bonus. These machines are super cool, and Jesse needs to do a video on his ring spinner, so be sure to check out his channel and let him know that you can't wait to see it. And with nothing left to lose, we all went at it full tilt. Enjoy.
Whatever. This one's meshed together.
If you'd like to build your own plastic ant weight or any other combat robot for that matter, I highly recommend it. You can watch one of these videos next if you want to keep getting your fix of robotic destruction. A big thanks to PCBWay for sponsoring this video, and I'll catch you again very shortly here on Maker's Muse. Bye.